Okay, so for this example, we're working some sort of structure here. It's basically a stepped shaft. So it's got a diameter of d on the right-hand side there, and the left-hand side has a diameter of 1.5d. And then it is, it had been kind of turned in a manner that using I guess a cutting bit that had a radius of 0.1d. So basically, we know the ratio of the sizes of these um, of yeah, the ratio of the sizes of these things, but we're trying to find out if we have to apply some sort of a load to it. Kind of what does d and uh, the rest of the dimensions have to be as a result. So made out of a brittle material. This particular brittle material has a ultimate strength and tension of 100 megapascals and ultimate strength in compression of negative 400 megapascals. So if we want to have a safety factor of 2.0 at that shoulder, what sort of what does that dimension d that's driving everything need to be? So and as for the loads, so basically we're mounting one side to a wall and then applying 3 loads to it. So we've got an axial, it's at 200 newtons coming out. We've got a bending moment, so that'll be like a bending moment about the z-axis. Positive bending moment about the z-axis. It's 1,000 newton millimeters. And then we got some torque. So that one's going to be 5,000 newton millimeters torque, about the x-axis with our x, y, and z going like that. So we know that kind of the we're asked to investigate kind of a failure for at the filleted shoulder. So we know that the critical location is going to be kind of at the bottom there because we have a tensile axial force and we have a positive bending moment. So a bending moment like this is going to be causing it to bend in a shape like this. So that's going to cause compression at the top and tensile at the bottom in order to stretch stuff out into place. So our critical location's at the bottom there, where the tensile stress there combines with the tensile stress from the bending combines with that of the axial. So the axial, and what the actual stress is for the axial, is going to be KT times P over A. Again, it's a brittle material, so we definitely need to know what our KT is. Need to take our stress concentration into account. So the P is 200 newtons, and then the A is pi over 4 d squared. Obviously, I moved the 4 up here. Oh, I need to scroll down a bit, don't I? Yeah, 200 newtons divided by pi d squared over 4. So we do know that the r over d is 0.1, and the d over d, the big D over little d, is 1.5. So again, going to our stress concentration figures from juveniles, we're able to look up what that KT should be. So based upon that combination, we should expect to have a KT of approximately 1.89. So multiplying everything out, the 1.89 times the 2000 divided by pi sorry, 1.89 times 2000 times 4 divided by pi gives us 4,813 newtons per d squared down here. So we got that. So that's our axial. We got our bending as well. So bending. So the bending stress is kT times 32m divided by pi over d. Sorry, divided by pi d cubed. And again, that's basically just them already substituting in the values for the values for I into the equation. If you're wondering, the nice thing about the charts in juveniles is that they include the nominal stress equations on the chart, so you can just go straight there and write that down instead of having to remember what the formula for bending stress is. So there we've got our kT times 32 times 1,000 Newton millimeters divided by pi d cubed. KT in this instance with the R over D of 0.1 and the D over D of 1.5. That's going to be approximately 1.68, eyeballing it. But I don't have the chart open right now, but you can go look it up if you want. Anyhow, so again, multiplying that out, the 1.68 times 32 times 1,000 Newton millimeters divided by pi, that gives us 17,112 Newton millimeters per the d cubed. And then we got our torque as well. So for the torque, formula there is kT times the times 16t over pi d cubed. So our torque value there is 5,000 Newton millimeters. And of course we got our pi there. And then the kT value for that, again eyeballing it roughly, but it looks to me to be about 1.39. I generally try to kind of bump, when in doubt, bump it up a little bit. That seems to be a reasonably decent method of kind of being a bit conservative with your estimates, especially in instances like this one where you need to try to interpolate between the different d over d lines. But anyways, so yeah, multiplying everything out, 16 times 5,000 Newton millimeters times 1.39 divided by pi. That gives us 35,396 Newton millimeters per d cubed. So the thing here is that our axial and bending combine, because they are both normal stresses and they both have the same orientation. So again, based upon a coordinate system chosen here, both of those would be normal stresses in the x direction. Our torque, on the other hand, is a shear stress, obviously, and it would be, that shear stress, if we're, here, just 1 second here, zoom in a little bit. So again, if we are taking a section, kind of right here, the section the section we're taking is going to be the face of the section we slice is going to be the x face, and if we kind of look at that from this direction, so this is the positive x face, and we're applying some sort of torque around here. That at the bottom here, that torque is going to be kind of pushing pushing in this direction. So on this view, be kind of coming at it from the side. So that'd actually be a ZX shear. Be a negative ZX shear because a positive Z is kind of coming out of the page here, not into the page. That having been said, it's the only shear that's there, so and we're worried about calculating the magnitude and whether or not it's going to fail. So the directionality there isn't all that critical. Okay, so yeah, how much did I zoom in here? I think bit too much. Okay, so let's see here. So putting that on a plane stress element here, we've got our we got our normal stresses here, which is the combination of the 17,112 Newton millimeters per D cubed, and we've got our sorry, did I say axial? I meant bending. This is bending. This is the axial, the 4,811 newtons per D squared. X bend, and all of those, both of those combine in order to cause bending stress. Sorry, normal stress in the x direction. So we got those. We have the shear stress. So the shear stress again kind of acts on all four faces in that direction, in that orientation. Its magnitude is the 35,396 Newton millimeters per D cubed. So, when we're trying to figure out what our stresses are, again, we can just represent this. Say that these two things added together is sigma x, and if we were plotting Moore's circle, then the mean of that would be sigma x over 2, because we don't have any stress in the z direction. Oh, sorry, we don't have any normal stress in the z direction. So the mean of that would be sigma x over 2. The radius is that sigma x over 2 squared plus the value for the shear stress. And then I guess the 1 here didn't show up too well. That's supposed to be that's supposed to be our sigma 1, which is equal to the sigma x over 2 plus r. The sigma 2 is equal to sigma x over 2 minus r. And then obviously that's a bit of a complicated calculation when we're trying to solve for d, but it's ideally suited for a spreadsheet. So basically I went ahead and took a Google Sheets spreadsheet to solve for what our sigma 1 and sigma 2 is in terms of d. So with d as an input. In this instance, we know that sigma 1 is always going to be positive and sigma 2 is always going to be negative. So that would be kind of ideally suited for the simplified Moore's failure criteria, which again, that's the one where we have like this, So like this is our sigma 1 axis, this is our sigma 2 axis, this is the sigma ut, and then we got the sigma and we got our sigma uc here. So yeah, using ideally suited for the simplified Morris failure criteria. So again, just keeping in mind that kind of calculating the safety factor there depends upon basically, zoomed in a bit too much there, basically kind of figuring out where our operating point is. So again, if our operating point is going to be somewhere along, so for each particular D, we can figure out kind of what the sigma 1 and sigma 2 is. We can plot that position. We know it's going to be somewhere in this quadrant. We can plot its position, and then we can figure out the ratio of the size of this line here versus the size of the line that goes all the way, actually here, let's use blue for that, versus the size of the line that goes all the way to kind of the edge of the failure envelope. Okay, so let's zoom back out here. All right, so again, the way the geometry of that works out is that 1 over our safety factor is equal to the sigma 1 value divided by the sigma ut plus the sigma 2 value over the sigma uc. And then essentially, again, implemented that in our Google spreadsheet, and I was able to figure out that if you have a D of 12.34 millimeters, then our safety factor there is 2.002. So rounded that up to 12.35 millimeters, since, might as well. And then I highly suggest taking the time to verify the spreadsheet accuracy by doing some hand calculations. So just punching in the 12.35 millimeters into the various spots where it shows up in the calculations that we set up, and ran through that. So that gave us an axial stress of 31.56 megapascals, bending stress of 9.08 megapascals, gives us a sigma x of 40.64, sigma mean of 20.32, shear stress of 18.79 megapascals. Take these two numbers, plug them into our R equation here. That gives us an R of 27.68 megapascals, which gives us a sigma 1 of 48 and a sigma 2 of negative 7.36. And then calculating our 1 over the safety factor, 48 divided by 100 plus negative 7.36 divided by plus negative 7.36 divided by negative 400 leads to us having a safety factor of 2.006. So, of course, obviously some rounding errors there, but seems to verify that. I highly suggest, if you're using some sort of spreadsheet or what have you, or some sort of calculator to solve for what your D values are, I highly suggest doing this hand calculation verification step because, well, I'll guess what? When I discovered 3 separate errors that I had made when setting up the spreadsheet that I'd made. So yeah, it is highly recommended that you verify your answers after the fact. And yeah, that's about that. And that is about all that we'll be doing for stuff that is purely stress concentrations and safety factors. The rest of it will be applying applying that to bolts, or applying it to welds, or applying it to shafts, and so on and so forth. So you are definitely expected to be able to take these concepts and apply and use them in the rest of the course, which I guess shouldn't be too shocking. So yeah, see you folks.